Good afternoon, class. Welcome to EGM 212, Engineering Mathematics 2. And we are still discussing differential equations, the topic we had started last time. But today we'll move a step further and look at the Bernoulli equation. But before we look at the Bernoulli equation, which is an extended form of the linear differential equation, I'll love to make a quick recap of what we did last time. So last time we looked at linear differential equations, and we stated that linear differential equations can be represented in two forms, either the dy over dx plus py is equal to q, where p and q are functions of x, or dx over dy plus px is equal to q, where p and q are functions of y. Then we also stated that the general solution for a linear differential equation is given by y multiplied by if is equal to the integral of the product of q and if with respect to x plus k. Then we also had stated that if is known as the integrating factor and is given by e raised to the power of the integral of p dx. So then the standard general solution we said was going to be y multiplied by the e raised to the power the integral of p with respect to x is equal to the integral of the product of q and e raised to the power integral of p dx with respect to x plus a constant. So this is the general solution as we had discussed last time. Then we went on and solved three different examples. So there was the first example, which is dy over dx plus 5y over x is equal to 2x cubed. So we're able to show the different parts of that equation because it's already in the standard format. So we got the integrating factor and found it to be x to the power 5. Then we had, at this stage, we knew we had everything that we needed to come up with a general solution. So this is what the general solution gave us. This was the final answer. Okay, then we went to the second example. Yeah, oh, sorry. Then on the previous slide, we said you needed to complete. So we ask that you complete this solution. There's that part there that needs to be worked out. Okay, then on the second example, we said first you multiply throughout by 2, and multiplying throughout by 2, it gave us an equation that looked like this: dy over dx plus plus 2xy equal to 4x. Okay, so we got this equation simply by multiplying throughout by 2. Why did we multiply throughout by 2? Because we wanted to get rid of the fraction, the 1 over 2. So to get rid of the fraction 1 over 2, we multiplied throughout by 2, and it gave us this. So it's from this that we got these different values. The p, which is 2x, the 2x here. Then the q, which is 4x, the 4x here. Yeah, so then the integrating factor, it gave us e raised to the power x squared and the general solution gave us this expression. So equally here, we ask that you proceed and work out this equation, because there's this part which is not completed, and we advise that you use integration by parts. Okay. Then we also did the third example. Which luckily is also already arranged, or it was also already arranged in the standard format. So it was very easy for us to tell which one was P and Q. So for P, we found that it was cos x over sine x. Q was e raised to the power cos x. So the integrating factor then gave us sine x. Okay. Then the general solution was simply plugged into the general formula, and it gave us y sine x is equal to the integral of the product of e to the power cos x sine x dx. Yeah, so after using integration by parts, this is the final answer. Okay, so this was the end of last time's discussion. So today we shall move a step further into what we call the extended form of linear differential equations, which is the Bernoulli equation. So the Bernoulli equation takes the form dy over dx plus yp is equal to y raised to the power n q. This is the standard form of the Bernoulli equation. So in this case, P and Q are both functions of x. Sometimes it may also present itself as dx over dy plus xp equal to x raised to the power nq, in which P and Q are functions of y. Okay, so let's look at the methods of solution of this extended form of differential equations, or linear differential equations, known as the Bernoulli equation. So given the differential equation dy over dx plus yp is equal to y to the power nq, the following are the steps that we need to follow. So step 1, divide throughout by, is supposed to be y to the power n. Divide throughout by y raised to the power n. Okay, if we divide the given expression by y raised to the power n, we'll get this expression. Then, if we let v be equal to the coefficient of p here, if we let v be equal to the coefficient of p, and then differentiate v with respect to x, we'll get dv over dx is equal to 1 minus n y raised to the power negative n dy over dx. Okay, that's step 2. Step 3, we divide both sides by 1 minus n. Dividing both sides by 1 minus n, what do we get? We get the expression 1 over 1 minus n dv over dx is equal to y raised to the power negative n dy over dx. Step number 4, we substitute, substituting into equation 1 the above. Into equation 1 we have, let's get to equation 1, you see, in step 1. Yeah, so step 1, we have y raised to the power negative n dy over dx. Y raised to the power negative n dy over dx, which is just the same as what we have here. y raised to the power negative n dy over dx. So if this is equal to this, then it's just the same as having the left-hand side plugged into step 1, which is this part. This is the left-hand side of this equation. So we'll say the left-hand side. The left-hand side is what we have here. Okay. So then this V from step 1, we're able to tell that this is where we said let y be equal to let V be equal to y, then 1 minus n. Yeah, I think this is quite clear. So multiplying throughout by 1 minus n here, I don't know why some of these are not displaying. 1 minus n. Multiplying throughout by 1 minus n, we'll get this equation. Then this equation, by visual inspection, we're able to tell that it actually is a linear equation with v as the dependent variable and can be solved using the method of solution of linear equations that we did the previous time we made. So we have dv over dx plus 1 minus n in brackets, then vp is equal to open bracket 1 minus n close bracket q. So the dependent variable in this case is v. So we have v here and v here. Yeah, so these are the dependent variables, and from this we can tell that it actually takes the form of a linear differential equation, okay, which is of the form dy over dx plus py is equal to q. This is the standard format of a linear differential equation. Okay, so now let's see if we can apply this Lent procedure. So solve the differential equation dy over dx plus y over x is equal to x squared y raised to the power 6. So this equation, luckily, it's already in the Bernoulli format. Yeah, you've seen the y is being raised to the power 6. So for the solution, the solution is first we divide throughout by y raised to the power 6. Dividing throughout by y raised to the power 6 will give us y raised to the power negative 6 dy over dx plus y raised to the power negative 5 over x is equal to x squared. Yeah. Then from here, we are simply following the same procedure. We let v be equal to y raised to the power negative 5, which is the y raised to the power negative 5 there. So now we differentiate v with respect to x. Differentiating v with respect to x, it gives us this expression. Then from here, we get back to the, we divide both sides of this equation before we get back to the top. We divide both sides of this equation by negative 5. So if we divide both sides by negative 5, we're going to have the left hand side of this the left hand side of this equation is going to be this one. The left hand side of dv over dx is equal to negative 5y to the power negative 6 dy over dx. After dividing both sides by negative 5, we're going to have the left hand side this, the left hand side. So the left hand side will give us this part. So why are we putting it here? It's because after dividing both sides by negative 5, what will remain on the right hand side of the equal sign is going to be this part, the y raised to the power negative 6 dy over dx, which is this part. So if y raised to the power negative 6 dy over dx is equal to negative, which will now be here, negative 1 over 5 dv over dx. If these two are equal, then it's just as well we get the negative 1 over 5 dv over dx, we put it here. And where there is y to the power negative 5, we put our v, because that was our initial assumption. We said v was equal to y to the power negative 5. So if we put it like this, then we transpose and move the variables, you realize that you have dv over dx minus 5v over x is equal to negative 5x squared. So from this stage, we can apply the process of linear equations. You can solve using linear equation. Okay? So the integrating factor, it gives us 1 over x to the power 5. Then the general solution gives us v over x to the power 5 is equal to negative 5, the integral of the product of x squared and 1 over x to the power 5 with respect to x plus k. Then from here, we have that simplification, then the final answer. Not necessarily the final, because we still have v appearing. And in the given equation, we did not have any variable named v. So the v was just brought in. Yeah, we had assumed that v, or we let v be equal to y raised to the power negative 5. So what do? We slot this value back. Where there is v, we replace it with y raised to the power negative 5. That is going to be our final solution. Okay, so here we are saying complete the solution, bearing in mind that the initially we had let v be equal to y raised to the power negative 5. Okay, so where there is v, we simply put that value. Okay, so now we have prepared some problems which we expect each one of you to work out and submit by next lecture. By the time we have our next lecture, you should be able to submit. You can either submit via WhatsApp or online on the students portal. You can be able to upload your solutions. So there are 6 problems that have been prepared. Okay, these are a mixture. They are both the linear differential equations as well as the extended form of linear differential equations. Okay, so today we end our lecture here. The the title of the lecture was linear differential equations and extended form, which is the Bernoulli equation. Okay, so the lecture ends here. We shall meet next time. Goodbye.